All right, let's get started. So good morning, everybody. Welcome to the MAERI tutorial. So we're going to be talking about enabling this, rapid design space exploration and prototyping of DNN accelerators. So I'll just start by introducing all of us. So I'm Tushar Krishna. I'm an assistant professor at Georgia Tech. We have Michael Pilawar, who's a senior research scientist at NVIDIA, and we also have Hyokjun Kwon, who's a PhD candidate at Georgia Tech. And I also wanted to acknowledge the people whose technical contributions have directly or indirectly impacted all of the work in this tutorial. So Joel, Vivian, Yushin, Angshu, and Anand. Right. So this is going to be just a rough outline of the schedule. So I kickstarted the things with an intro and background. It's going to be pretty short. I just wanted to kind of give an overview of what the tutorial will be about and give you just the relevant background before we go into the two tools. So we're going to be presenting two tools, Maestro and MAERI, and I'll give an overview of what those are. And of course, there's going to be some hands-on exercises and we wrap up at the end. Right? So this is, as I said, the outline of what I'll talk about in the first few minutes. So what this tutorial is about, right? So of course, we're basically in the era of deep learning. Deep learning applications have shown remarkable accuracies across vision and speech processing. And the deep learning landscape today looks something like this, right? So you start with a deep learning model that you want to create. You iterate over it, you send it out for training, and of course this is a feedback process. Once you have a trained model, you send out the weights to edge devices where inference is being performed, right? And since you really want energy efficiency on these edge devices, and the trend has become to add custom processors for DNN acceleration on these edge devices, there's been a lot of work recently on developing custom accelerators, both from industry and academia. Right? So, of course, one of the key things that enables such a landscape is design tools. So, for model creation, there's tools like TensorFlow, Caffe, PyTorch, and so on that let you kind of iterate over and create models very quickly. For training, there's software packages across CUDA and Intel and other vendors that let you kind of perform large-scale training. Even for inference, there are tools that let you kind of optimize your neural network for your target platform. But on the hardware end, to actually design custom accelerators, unfortunately, our community doesn't yet have a lot of design tools to help you do rapid design prototyping, which is kind of what we want to target with this tutorial. So we're going to present these two tools that are essentially aimed at this space, right? So again, just to set some context, so we have like the sister tutorial on just hardware architectures for deep neural networks that Joel, Vivian, and Yushin run. They run at last ISCA, Micro, and so on. So that tutorial kind of goes over an overview of deep neural networks, surveys recent DNN models, surveys recent DNN hardware accelerators, and talks about novel optimizations for code design, benchmarking metrics, and so on. This tutorial is more on tools, so practical tools to enable DNN accelerator architecture, design space exploration, mapping strategies, and hardware prototyping. Right. So just to kind of set context, as I said, we will go into a very brief background of DNNs, but the focus more is on how do you design accelerators targeting DNNs. So just a quick note about software setup. So of course you have the Wi-Fi information that's up there here. We have a VM with the with the Maestro and MAERI code. So we're going to be passing around pen drives now. So you can install these on your laptops, copy both the .vbox and VDI file. There's a directory that does that. So if you have VirtualBox installed, then you can directly launch the VM. Otherwise, we also have the VirtualBox files. And the password for the VM is MAERI 2018. It's also listed on that screen there, right? So this will just help you with some of the hands-on exercises that we have if you wanted to get your hands dirty. We will be also doing demos throughout, but this will be useful to run. Also, we're going to be passing around sign-up sheets. So just this is the first iteration of the tutorial, so we want to get a sense of what the interest was. So please sign those as well. Okay, so yeah, if you have any questions about the software setup, we will be available, and like once we move on to the next version, before that we can do that. But at least it will be good to kind of get started on that.
And if you have a USB 3 port, make sure you plug into the USB 3 port. It'll be a lot faster.
It'll be a lot faster. Yeah. All right. So with that, let me give some, again, relevant background on what we're going to talk about. Right. So what is a deep neural network? So at a very high level, it's basically a computation platform that's modeled similar to the human brain, where you have this notion of neurons that are interconnected with synapses. So using those same terms, the reason why we call these deep neural networks is because you often have multiple layers in between the input and output layers. So the more layers you have, the more accuracies you often see, which is why these are called deep neural networks. Each of these edges or synapses often have weights associated with them, which essentially enable a neuron activation. So if I have neurons which have produced the values x1, x2, x3 here, these are sent through these weights, and the next set of neurons essentially compute a weighted sum and then pass it through an activation to generate the next value, right? So that's the very, very high level computation model that we need to care about to understand most of the tutorial. As I said, there's of course a lot of theory behind this, which I would encourage you to go and look at other tutorials on how all of this works. So that's essentially the idea of a neural network. So where does this fit in within, again, the modern deep learning landscape? So I talked about kind of, these 3 steps in the landscape today. So I mentioned we're going to be focusing on inference, and let's see what happens in inference. Let's say I give an image to a deep neural network which has multiple layers. So there's often a lot of convolutional layers in deep neural networks today, which essentially allow you to extract features from your image. And once you've extracted features, you send them through some more layers to summarize these features. And finally, in this case, if it's a very accurate DNN, it will be able to identify this as the Intercontinental Hotel in which we are right now, right? So this is essentially the idea of this whole flow. And why do we need DNN accelerators to run something like this? Well, there's actually millions of parameters or weights in most of the DNNs today. So this is just a snapshot of some of the recent DNNs, ResNet being one of the most recent. And you can see there's essentially millions of weights here. And so what that means is you have millions of computations. So I talked about the multiply, accumulate, or the weighted sum as the basic computation unit. You have to perform millions of these if you wanted to do inference in close to real time, right? Which essentially necessitates a lot of parallel compute. And you have a lot of data movement, because obviously all of this cannot fit on a chip. So there's going to be a lot of data movement from memory to the chip and within the chip. So you essentially have to worry about data movement costs at various levels of the memory hierarchy. As computer architects, we're kind of aware of these various costs. And so all that means you really need to design things that reduce energy, right? So what's happened within the field in terms of trying to address these two challenges is there's been an emergence of spatial, or often called data flow style accelerators. So the idea is you have an array of these large processing elements connected by some memory hierarchy. And so the way you solve the challenge of millions of computations is essentially you try to spread these computations across hundreds to maybe even thousands of these ALUs. And to tackle the data movement challenge, you try and reuse data as much as possible within the array. So you try and forward the data locally between these ALUs rather than going back and forth between memory. So again, at a very high level, these are kind of the 2 ways with which you try and address this challenge. And we'll go into more of these details later. Right, so this is kind of the setup that we'll be looking at. So of course, so as architects, this brings out 2 hardware design challenges. So first is, how do you actually map all of these millions of computations over the limited compute and memory resources that you have, right? Or that's also known as data flow. And then how do you actually design this accelerator so that it can efficiently work across all of these DNNs and across all of these possible data flows or mapping strategies? So these are the 2 things that we're going to be addressing in this tutorial. So the first tool we'll present, called Maestro, essentially focuses on the first aspect, on how do you essentially come up with the most efficient data flow for your accelerator substrate. And the second part of the tutorial focuses on a tool called MAERI, which is essentially an accelerator that lets you efficiently map these layer types. So as a quick preview before we go into those details, so on the Maestro end, the idea is you essentially have some target DNN, you have some accelerator architecture, and you have some data flow that we let you specify. So these are taken as input parameters into the tool, and the tool essentially gives you statistics like what are the memory access counts across the memory hierarchy, what's the roofline throughput you need, what's the interconnect bandwidth you need to support these kinds of things, and you can also plug it into an energy model to get energy analysis. So this is kind of a snapshot of what Maestro lets you do. And the second tool, MAERI, essentially works in this manner. Here, this is more an open source RTL for flexible DNN accelerators. So again, you give the description of the layer you want to run on the accelerator platform, and you give it a description of the resources that you have in terms of the bandwidths and the number of PEs. There is a front end with a library of RTL building blocks that we provide. This is written in BlueSpec, so there's a BlueSpec compiler that essentially generates RTL and gives you synthesizable Verilog that you can put on an FPGA or run it through an ASIC flow. In addition, it also lets you do simulations and lets you do a design space exploration to get a sense of how much runtime would this take, what's the distribution of the number of weights that were sent, inputs that were sent, and so on, and what's the counts across the various levels. So you can kind of go back and tune your RTL to give you the accelerator you need for your target area, power budgets, and so on.
And the simulation for that is much faster than simulating the Verilog.
Yes, exactly. So this is kind of the key benefits of BlueSpec. So this is more like a C program. So the simulation will be much faster than actually having to simulate the Verilog. So this is kind of why we have kind of these two flows here, which lets you get very fast results. Yeah. So with that, welcome to the tutorial. So what I'm going to do now is, again, as I said, this is kind of the outline. So my part is done, and now I'm going to switch over to Michael, who's going to essentially present the first tool, which is Maestro.